Hello everybody, this lesson is going to be the intro lesson for learning how to draw what we call Lewis structures. Sometimes they're called dot structures or diagrams, sometimes they're Lewis dot diagrams, kind of any combo of those you can find them being called. So we're going to do a little bit of an intro, cover some basic concepts first. Then we're going to have a second part where I teach you how to draw things with single covalent bonds. And then we'll have a third part of the lesson where I teach you how to draw double and triple bonds. The first part, this intro part, is going to be on the PowerPoint, but then the rest of the lesson I'll do under the document camera with pens on a piece of paper. Since trying to do this in a PowerPoint is not easy, it's a lot easier to draw it. Okay? So let's get started. When we draw these structures, it's important to know that we're only going to be drawing the valence electrons. Remember, the valence electrons are the ones on the outside in that highest energy level. And so the reason those are the ones we're going to draw is because they're the ones that are on the outside that are available for bonding. When you have an atom bump into another atom, the bond that will form will be on the outside of the molecule, and so those valence electrons are the ones that are being utilized. So you're going to have to know how many valence electrons each atom has in the molecule. You're going to add those up and you find out how many valence electrons altogether are available for your picture to draw. Remember that we get the number of valence electrons from the periodic table. If it's in group 1a, it has 1 valence electron. If it's in group 2a, it has 2 valence. 3a has 3 valence, etc. Remember, we're not going to worry about the D block. We're not going to worry about the F block. They don't follow our patterns. So that numbering system that uses the A's is the one that we'll be using for finding the valence electrons. We're going to have something called the octet rule. You're going to notice that I put it into quotation marks because it's not a very good rule. The idea here is that most atoms want to have 8 electrons to have a nice full valence shell. The problem is this is broken a lot. For a rule, it gets broken sometimes more than it gets followed. So it's a good starting point, but you have to understand that when we say there are exceptions, this time they are common exceptions. I don't often make you learn the weird exceptions and the breaks in the pattern for things, because this is just a high school level class. But with Lewis structures, because these are so common, we do have to know these exceptions. I personally wish they had named it the octet suggestion or something like that, but we do tend to call it the rule. So you do have to memorize these. And you have to understand there may be some that you come across that are not on this list, but these are the ones that break the rule more often than they follow the rule. Hydrogen can only have 2 electrons. After that, it's very full. It's much too small to have up to 8 valence, so once it has 2, we consider it finished. Boron is also pretty small, and so it's going to have typically up to 6. You may sometimes see boron take 8 electrons, but it's not as common as 6. Phosphorus and sulfur can make what we call an expanded octet. Anytime you have more than 8, we call it expanded. Other things can do this too, but we call these common exceptions for phosphorus and sulfur because when I see those in a molecule, I'm going to assume they have more than 8, and if they don't, then I might be surprised. They can have 8, they don't have to have 10, they don't have to have 12. So you can kind of see that these common exceptions are ones that you should assume this is what they make unless it needs to be otherwise. If we want to draw the Lewis structure for a single atom, we put the symbol and then we put a dot to represent the valence electron. So you're going to notice that we go along the sides of a box. If you imagine a box being drawn around these, we put the dots on the 4 sides of the box. We spread the electrons out. That's going to help us when we start trying to figure out the overall shape and geometry. So that's why we want to keep our dots nice and tidy on the 4 sides of the box. Lithium has 1, beryllium has 2, boron has 3, carbon has 4, and then you get to the point where you have to start doubling them up. Kind of reminds you of when we were doing orbital diagrams, right? You spread them out and then you double them up. Okay, so you can see that here all the way up to neon, which has 8, nice and full. You'll notice that some of these are paired and some are single. Sometimes we'll ask you questions about that. If we ever want to draw a Lewis structure for an ion, we have to adjust the number of electrons. And we also have to have some way of telling people that we've adjusted it. We don't want them thinking that's what it would normally look like. So oxygen normally has 6 valence electrons, but when it forms an ion, when it makes oxide, it becomes O2-. It has 2 extra electrons. So instead of having 6, it's going to have 8. I draw the 8 electrons. I put square brackets, not parentheses. That is important. It needs to be a square bracket. And then you put the superscript with the charge up top. That tells people that this oxygen normally doesn't look like this, that this has been turned into a 2- ion. You can see the same thing down here with nitrogen. It's normally going to come with 5. Now it has 8 because it gained 3 extra electrons. I draw the 8 valence electrons, I put square brackets, and I put my charge up top. So that's how we would draw an anion. Drawing cations is a little bit stranger because we have to think about what they looked like before, what they looked like after, and we have to kind of think about how we're going to represent that when they've lost electrons. So, we still adjust the number of electrons because of the charge. The thing that's important to remember is that if we lose all their valence electrons, they're going to drop down to the previous level, which is already a full shell. So for example, magnesium has 2 valence electrons normally. It has 12 electrons total. If it loses these 2, it's going to drop down and it's going to look kind of like neon, right? It's going to have 10 total. But we're trying to draw what the original valence shell looked like. So even though magnesium will still have a bunch of electrons, and some of those will be on a new valence shell, what I'm trying to draw in my picture is how it looks compared to where it started, its original valence shell. So its original valence shell is now empty. And so I'm telling people it lost those original valence electrons. So the nice thing about drawing cations is you don't have to draw the dots, right? Because it's not gonna have any dots in here if it's lost them. So the cations are a little strange because you gotta remember that we're really trying to show the original shell here. If we want to draw an ionic compound, it's kind of nice. We just put the 2 things next to each other and we're all finished. So you can see here, I drew my cation for magnesium. I put the charge. I draw my anion for the oxide over here with the charge, and I just draw them next to each other. It's different than a formula because in a formula we wouldn't write the charges anymore, right? But what we're trying to show here is we're trying to really show the structure of what's happening, and the structure of what's happening is we have a positive ion and a negative ion, and so we want to leave those charges here. Now, if you have more than one ion like this, you have 2 of these fluorides, what you can do is just use a subscript to tell people how many of them you have. I've seen teachers who don't let you do this. I've seen teachers who make you draw 2 of these fluorides. I don't feel like that's necessary. I feel like if you can show me what one of them looks like and you can tell me that you have 2 of them, that's completely fine. Okay? All right, so when we start drawing our molecules, we're going to have a set of steps. And what I've done on this slide is I've kind of shrunk the list of steps down into fewer words. And I've highlighted certain ones in red. Normally, what I would do in class is we do a lot of call and response type work, where I say step 1, and you would all shout at me, count. And I'd say step 2, and you'd say place. Step 3, single bond. Step 4, full shell, etc. On the glue-in that you have for your notes, you have a more extensive list of steps with some extra bits thrown in here. So this is just trying to show you the key words that I'm going to kind of ask you to shout out at me. Okay. So take a moment and get those ones in red down. What you could do on your glue-in is highlight them so you don't have to recopy this entire thing. One of the things that drives me completely bonkers about this topic is that almost all the teachers I've seen teach this tell people, just put dots on your paper and move them around until it works. Well, that's crazy, okay? That's guessing and checking, and that's not how we do things, okay? There is a systematic way that you can go about doing this that will work every time. And to me, if I had a teacher tell me, if you do this every time, it will work, I would for sure listen to that. But no one ever does. People just put dots all over the place and they don't follow the steps and they get things all wrong and they get super confused. And then they come to me and they say, I don't know why this is wrong. And I say, okay, well, let's do step 1 together. Let's do step 2. Let's do step 3, etc. And then suddenly they get it right. So all I can do is show you how to do this. I can give you tools like the little glue-in, like our little highlighted words here. I can give you practice. I can be available for help, but you have to choose to listen to me or not, right? You have to choose to follow these steps or not. Please, please, please don't just randomly draw dots on your paper, okay? So one of the things I do highly suggest is that you use pencil, because part of these steps that we're going to use is going to require that we go back and we make some changes to our first attempt sometimes. And so you do need to use pencil for that, okay? So step 1, count and sum your valence electrons. That's straightforward. Use your periodic table, add them all together, okay? Placing your atoms is a bit tougher. There are going to be some suggestions that I have, but they're not always going to work. They're just suggestions. Sometimes you may have to try a couple different ways of placing your atoms, but the nice thing is there won't be very many options. The third step is that we're going to always assume that it's the simplest molecule possible, because it usually is. Most things have single bonds. So why don't we just assume they have single bonds unless we realize they don't? So we're always going to start with the simplest option. We have to single bond things or they'd be floating around by themselves. So we have to connect them. So connect them in the simplest way possible, which is a single bond. Then what we're going to do is, because this is just a drawing and I'm just trying to draw some model to see if it works, I'm going to give every atom however many electrons it would like to have a full shell. Just going to say, hey, the simplest option is everybody's happy, right? Then I do step 5 and I count how many that I used. And if I didn't use enough, then I'm going to put the extras on the center atom. That's typically where the extras will go. If I recount and I've used too many electrons, right? Because step 1 tells me how many I'm allowed to use. Step 4 was how many I wished I could have. So if I used too many in step 4, then I'm going to have to start making double and triple bonds to reduce the number of electrons being used. So we kind of draw it a simple way. We check if it works, and then we start fixing things systematically. Before I kind of show you some examples under the document camera, I'm going to give you some suggestions for where we place our atoms. This, I think, can be the hardest part until you've started to see enough examples to realize that a lot of these are kind of similar to each other. One of the most important rules is that hydrogen has to go on the outside of the molecule. Hydrogen can only make one single bond. It can only have 2 valence electrons. And so it kind of functions as a dead end, or we say it terminates the molecule, or it caps it off, because it can only make one bond. So in this example, if I have H2O, I cannot put the hydrogen in the middle like this, because then if I connect these atoms, I can never connect my oxygen. Or if I connect these two, I can never connect this other one. So I have to put the hydrogens on the outside so that they only make one bond. Another suggestion is that the least electronegative atom should go in the center typically, unless it's hydrogen. Rule number 1 comes first. So you put the hydrogens on the outside, and then after that, if there's choices, the least electronegative goes in the middle. So the reason for this is that it allows the molecule to have the electron density be pulled towards the outside of the atom. If the more electronegative elements are on the outside, they're going to end up with the electrons having more elbow room. They're going to be able to spread out more. They're not going to feel as crowded, and you're going to minimize the repulsions. So you want to put the least electronegative in the middle of the molecule so that it's not pulling those electrons inwards. The last one is the hardest because it takes a little bit of judgment to decide what the most symmetrical option would be, and it's why sometimes you may draw a molecule where the number of electrons work, but I say mine is better. And that is hard because you have to always draw the best version. There might be lots of versions, but you're trying to find the best version. The interesting thing is, in nature, typically the one that's most symmetrical is going to be the most stable, and it's going to exist in the highest, abundance. So if we had these 2 molecules, they both exist in real life. This one is more symmetrical because it has a double bond on each side, whereas the one up here has a double bond and a single bond, so that's not super symmetrical. So while this may exist in real life, there's going to be a lot more of this bottom one existing. It's going to be more common. So we always are trying to find the way to draw the best structure possible. And sometimes it can't be symmetrical. Sometimes that's just not an option. We have to understand we're always trying to do the best we can. Sometimes that means really ugly structures that break all the rules, but it might be the best we can do. You have to be comfortable with that. You try your best to make it look good. If it can't look good, then you got to start drawing an ugly structure, right? So the symmetry is the one that probably gets broken the most. Okay. So that's kind of the first chunk of this lesson. I'm going to switch to the document camera. I'm going to record that as a separate video, so it will have a separate link on the YouTube channel. And then I'll put all of the links to all of the parts at the end of this PowerPoint so they're all in one place for you. All right, that's it for now. Bye, everybody.